day, guys. You are welcome to Tpths.ng Center. So today we'll be taking chemistry. We are still continuing our series. And last class we were able to talk about the electrodes, and we learned a lot about the electrodes. Today we are going to be summing up all what we've learned so far, from electrode to oxidation number, half cells, and everything we learned earlier. And we are going to be treating something very, very important today. So I would like every one of us to please pay attention and also try to understand the concept here. So today we're handling electrochemical cells and electrochemical series. Electrochemical cells and electrochemical series. I recall when we were taking the last class, I had to show a figure where I was showing different electrodes, and I made mention of the fact that you dip a metal in an electrolyte. This is what happens and everything. And also I remember that I was able to more of like pave way for how this class is going to be last class. So today we are going to be talking about electrochemical cells. I want you to follow the slide and please pay attention also too. Now, the electrochemical cell, on what you can see about the electrochemical cell is that we consider a reaction medium where we have maybe a beaker, maybe two beakers containing two different electrodes. This does draw a rough sketch, something like this. So two different electrodes. What's the length? Now this is two different beakers, and we also learned that they will all come together to this is volts. This is the fast electric current around, and also recall that there's always going to be a salt bridge where different electrons move and everything. Now, so you can access something earlier on there. The flow of electrons. So a flow of electrons can be said between what? Two electrodes here. A flow of electrons can be said between two electrodes. And you can see that we also learned about electrode potentials. And we said that last class that electrode potentials vary for different metals. So the flow of electrons between these electrodes, knowing that the electrode has different electrode potential, is what is also known as what they call electrochemical cells. Now, the chemical cells does one thing. It converts chemical energy to electrical energy. Electrochemical energy, electrical energy. So it can also be called a chemical cell, galvanic cell, or voltaic cell, depending on how you are moving the flow of electrons. The flow of electrons determines where is it coming from, where is it going to. So those are the things we need to also note that in this part of this topic. Now, in a chemical cell, what do you see in a chemical cell? First, we need to know that we have what they call an oxidation half cell. An oxidation half cell. Let's recall that earlier on we talked about redox reactions, and we need to know that in electrochemical cells, redox reaction occurs here very, very well. So in one of the electrode there, what goes on there is what they call oxidation. The other electrode is what they call reduction. So oxidation half cell occurs at the electrode, then reduction occurs at what? The other electrode. So does the flow of the flow of ions from the anode to the cathode, the whole movement is what leads to what we call electric what? Please understand. Now, first of all, we have what they call an anode. That is an example of what they call a zinc copper couple. A zinc copper couple. So we have an anode. Let's say that this is zinc, and let's say this is what? Copper. And this is the salt bridge from that diagram we have here. This is the salt bridge. And we know that in that place we have what they call zinc sulfate aqueous solution, and here we have CuSO4 aqueous solution. Now, what happens here is that the zinc electrode itself undergoes what they call oxidation. Oxidation. What is oxidation? Oxidation is the loss of electrons. Oxidation is the loss of electrons. What happens here is that zinc loses two electrons. You can look at the slide there. They said zinc electron undergoes oxidation and lose what? 2 electrons. So zinc loses 2 electrons to form what? Zinc ions. To form zinc ions. And when zinc loses an electron, the zinc electrode becomes negatively charged. The zinc electrode becomes negatively charged. And when zinc electrode becomes negatively charged, is known as what they call a negative electrode, or what we all hear everywhere as what? Anode. 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 The anode is the what? Negative electrode. Negative electrode. Negative electrode. Negative electrode. Now, the excess electrons from zinc, the electrons from zinc, so why you can see a salt bridge that connects the both of them together. So the electron from zinc, and they flow along the wire. They flow along the wire to what? To copper here. To copper. And what happens here that copper is electron deficient. Copper electron is electron deficient. And what happens here that the copper ions become reduced. The copper ions, they become what? Reduced. By how they become reduced? By gaining 2 electrons. Zinc lost 2 electrons. Copper will what? They become reduced and what? They gain 2 electrons. And when copper gains 2 electrons, what happens is that a metallic copper is what? Deposited at this electrode. Take that again. I take that again. That when zinc loses 2 electrons, excess of the electrons is in the solution there. So this set of electrons, they go to copper through the wire there. And when that happens, copper itself is electron deficient, is an electron deficient electrode there. What happens is that it gets reduced. It gets reduced by gaining 2 electrons. It gets reduced by gaining 2 electrons. When that happens, metallic copper is deposited on this electrode. And the electrode itself becomes positively charged. Becomes positively charged. Becomes positively charged. And we call that the cathode. 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 So, from what we've said so far, we can create what they call 2 half cells reaction. 2 half cells reaction. The first one, at the anode, you have zinc solid, giving us what? Zinc 2 plus 2 electrons. This is what? Oxidation. 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 It occurs where? It occurs at the what? The anode. 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 Copper 2 plus aqueous. They what? They get reduced by what? By gaining 2 electrons. And now it's making more sense. When they gain 2 electrons, what happens? A metallic copper is deposited at the electrode. This metallic copper here, copper solid, is deposited at the what? The cathode. At the cathode. And that's what you have here, cathode. Cathode. This is the reduction. Reduction. Now, when this happens, this is what they call half cells reaction. This is the reduction half. This is the oxidation half cell. Oxidation half cell. And this is the what? The reduction half cell reaction. So we need to know one thing, that chemical cells consist of what? It consists of the anode, the cathode, the salt bridge, the voltameter. And we also see the movement of, this is wire, which allows the movement of what? Of electron. So if zinc itself loses 2 electrons, this is the electrons here. If it loses 2 electrons, what happens is that copper itself, they gain these electrons. And when they gain these electrons, copper is deposited. It's deposited on this one, on this cathode. You see, it's deposited on this cathode. And that is what is making more sense here. It's making more sense. And we can now see that the flow of electrons, gain of it, the major thing there, what is going on there is what they call a redox reaction. Redox reaction. Simultaneous reduction and oxidation going on in this process. And when that happens, we need to now note something very, very important here, is that what? The oxidation half cell, reduction half cell, they both sum up to form what we call a net reaction. Net ionic equation. Net ionic equation. And what happens here is that we observe that 2 electrons are on the left-hand side and on the right-hand side. I think I did something like that last month. So what happens is that they both cancel out. They both cancel out to have zinc solid plus zinc copper 2 plus aqueous, giving us zinc 2 plus copper solid. This is what they call the net ionic equation. The net ionic equation. And with that, we've been able to what? To understand the reactions going on in the electrochemical cells. The reaction going on in the electrochemical cells. Next, we need to know is that we've talked about the anode. The anode is the negative electrode. The cathode is the positive electrode. And what we need to talk about next is the salt bridge. The salt bridge look like this bridge, like a bridge. It's the salt bridge. And what is the salt bridge? You can the salt bridge itself is placed between the two beakers. The two beakers is like creating what they call a connection between the anode and the cathode. Between the anode and the cathode. And what is the salt bridge? What is his main work that he's doing here? So that's why you need to understand that a salt bridge is what? Well, what you can see there is a porous partition. Is a porous partition. You can see what I highlighted there on red, so you can understand the functions of it. So it's a porous partition that prevents the mixing of electrons, because in this whole process here, electrons is moving left, moving right. So you need to understand that this whole process, there must always what they call a medium that can prevent the mixing of these electrons, and that's where the salt bridge comes into play. The salt bridge prevents the mixing of these electrons. Now, it's fine if you mix of the electron, but we need to also observe that. We need to also observe that it allows the passage of the tetrahydrosulfate 6 ions. So the passage of these ions, they move through this whole reaction. And why are they doing that? Because they want to neutralize the effects that is produced by the excessively what? Positive zinc ion. So it is trying to neutralize it because it's negative, positive, trying to neutralize it. And what is that? What does that mean? If you have negative, you have positive, it's trying to do what they call, it's trying to maintain what they call electrical neutrality of the reaction. Electrical neutrality of the reaction. Trying to make the reaction to be neutral. So that is what is going on in this whole process. And that's why salt bridge, one, they prevent the mixing of electrons. You can see the one I highlighted with red. They prevent the mixing of electrons. Number two, they maintain the electrical neutrality of the reaction. Mostly you see what I use the following is an example of a salt bridge, of a compound used in salt bridge. Example of that, you can see the example I used there. A piece of paper that is soaked in sodium chloride can act as a salt bridge. What are the popular ones? KCl, potassium chloride, and ammonium nitrate solution. They are very popular, very, very popular compounds that are used as salt bridge. Those two, KCl and potassium chloride, KCl and ammonium nitrate. Ammonium nitrate. Now, what are the examples of electrochemical cells? Fine, we learned about electrochemical cells. What are the examples of these electrochemical cells? Number one, the Daniell cell. Very, very popular cell. The Daniell cell. Daniell cell is even the Daniell cell I've been talking about here. The Daniell cell is the copper to zinc electrode. The Daniell cell, very, very popular cell in chemistry. So the Daniell cell consists of the zinc and copper electrode. And that's what I'm talking about today, the Daniell cell. The next one is the Leclancher cell. The Leclancher cell involves what? The anode is a zinc rod. The cathode is a carbon rod. The cathode is a carbon rod. And the electrolyte can be in two forms, either in wet or dry. If it's wet, it's ammonium chloride. And so electrolyte in ammonium chloride solution is either it's wet. If it's wet, that means it's in aqueous form. But if it's dry, it's not in aqueous form. So that is one thing you need to know about the Leclancher cell. Very, very popular. You can be asked the anode. What's on the anode of the Leclancher cell? You need to know that too. What is the cathode of the Leclancher? You need to also know that too. Zinc rod and what? Carbon rod. Other examples of electrochemical cells are, we have many of them. Even the nickel to cadmium cells is also an example. These cells that is running all over the world now, lithium cells, which is used in making batteries all over. Almost all the new folks now using lithium cells to make what? To make batteries. So lithium cells is also a good example too. We also have fuel cells, so that is used in bigger, that are used in very developed countries. So you can use fuel cells. So there are a lot of examples of electrochemical cells, and that is where we end for electrochemical cells. We now go to what? Electrochemical series, because now you see, let me take you to, we have what they call in most of our most elements can be separated or can be gotten from the or different places through an electrolytic method. Through an electrolytic method. But we need to know that it doesn't just happen. Why? Because fine, because you can use the chemical cells to do something like that does not mean that you need to understand the basics of everything. And that is what I'm talking about in the chemical series. The chemical series is something that we all must have seen one way or the other in our textbook. But we need to understand what the chemical series is all about. Now, the chemical series, you can see what they call, you can see in the chemical series, for those that, listen, for those that have gone through, I think, Babio is new school chemistry, you would have seen something like a tabular form or something, and you see arrows. So that is an chemical series. But what is an chemical series? And that is what that we are going to be talking about today. Now, anyone in the that's why I do talk. Bye. Potential, standard potential, rather. And I told you that each metal have their own standard potentials. They have their own standard potential. So these standard potentials of the elements can be arranged in a specific order. They can be arranged in a specific order. Such order is what is known as electrochemical series. Electrochemical series. Now, you see the series. What can we do from that series? Now, in the electrochemical series, you need to look at the top. You look at the top. At the top, let's say you look at the chemical series. At the top, this is the top, this is the bottom. The top and the bottom. At the top, what's at the top are what they call good reducing agent. Good reducing agent. Good reducing agent. That is strong electropositive, good reducing agent. That is strong electropositive metals. Your lithium, aluminum, see them there. Strong electropositive metals. Strong electropositive metals. And what do you see at the bottom is what they call good oxidizing agent. Good oxidizing agent. Good oxidizing agent. Good oxidizing agent. They are seen, good oxidizing agents are seen at the bottom. They are seen at the bottom. So they are seen at the bottom. Now, they are either called good oxidizing agent or strong electronegative element. Strong electronegative element. Strong electronegative element. Those are what you can see in an chemical series. Now, the next that you can see a diagram. Let me quickly explain that picture there. You can see lithium. You can see lithium. You can see potassium. Now, lithium, potassium are good reducing agents. They are found at the top. They are found at the top. So I'll cut the demarcation here. They are found at the top. So you can see lithium, potassium, barium, calcium, sodium, magnesium. Most metals of the group 1 and group 2 are found at the top. They're found at the top. And you need to also know that. Why? Because they are very good reducing agents, and they're also what? Strongly electropositive in what? In nature. Strongly electropositive in nature. Now, I created a demarcation here. Why? Because in as much as we have these metals here, there is a tweak to everything here. There is H2 here, hydrogen. The hydrogen has 0 electron volt. As that's the H2 has 0 electron, 0 volt rather, as the standard potential. And I can recall that in last class I talked about this hydrogen being this. Hydrogen has 0 volts as the standard potential. Why? Because it is the reference of all other metals in this series. All other metals get their standard potential based on hydrogen being their reference. So hydrogen is a reference in this part of in this chemical series. So ones that are above hydrogen, most of the times are very, very what? Positive. I'm very positive in nature. While those below hydrogen are good oxidizing agents. and strongly electronegative in nature. So that's it. So this hydrogen is the reference of everything. This series itself will not exist without what? Hydrogen. Because um all these standard potentials are gotten based on hydrogen. Based on hydrogen. So hydrogen is very, very important. And why you need to know that note that hydrogen is also a reference electrode. It's also a reference, what they call reference electrode. And hydrogen is called She electrode. So other metals get their potential based on what? Hydrogen, based on hydrogen as their what? Reference electrode. Now, the ones below the hydrogen, the ones below hydrogen can be said to be what? Good oxidizing agent. To be good oxidizing agent. And what you need to know that you need to understand some basics about everything. This chemical series, there are a lot about it. There are a lot. So, and you need to understand that, fine, in as much as you are having this occurring, now when you're having this occurring in this chemical series, you need to know what they call facts about the chemical series. What are the basic facts about electrochemical series? The facts about electrochemical series. Number one, the direction of the current flow from a simple electrochemical cell is dependent on the relative position of the two metallic electrodes on the chemical series. What does it say? Number one fact is that before you can pick an electrode, before you can pick an electrode, you need to note where is the position of this electrode on the chemical series. Because you need to note that the position itself tells us that it's going to be an oxidation half cell or reduction half cell. So that is why we need to understand that, oh, is this the location? That's why most of the time we have a pictorial view of the chemical series. Why? Because if you want to quickly analyze something, okay, this is where it's found in the chemical series. We need to also know that too. So that means that the metals that are higher up the series, they tend to be what? They become positive electrons. That means the ones that are up are mostly positive in nature. Like the signs are mostly positive in nature. If you look at the full electrochemical series, they are mostly positive. While if you go down, it tends to become what? Negative. It tends to become negative. And that will help us in picking, oh, is this oxidation? Is this what? Reduction. I can recall for what you learned about your E cell. E cell. That we said EMF. This is known as your E naught. Is equals to E right minus E left, or E reduction, I've added this today, minus E oxidation. E reduction minus E oxidation. That means the more positive value the standard potential of a metal is, the more that is the reducing it, that is the reduction potential. That is reduction. So if you have two, let's say you have an half cell A, half cell B, and this is more positive in nature, that means this will be the reduction half cell. If it is more negative in nature, this will become what? The oxidation half cell. So that's why you need to know the fact about the chemical series. That is the first fact. The second fact, the chemical series is also known as activity series of metals. Yes, it's also known as activity series of metals. That is true. That is true. So why is it like that? Because we believe that this is because metals are arranged in decreasing order of chemical reactivity. Yes, about chemical series are more reactive in nature. They are more reactive in nature. They are more reactive in nature. As you go down from that top, you observe, as you go from the top, going down, you observe that the metal's reactivity would decrease. Also, the non-metal, they are arranged in what they call increasing order of reactivity. That means non-metal that is found at the bottom, they are very, very reactive in nature. Very reactive in nature. And that is one thing you need to also note about this series, the chemical series. You must always note something like that. So the non-metals are arranged in increasing order of chemical reactivity, And this is because reactivity of non-metal is related to the readiness to form what? Negative ions. To form negative ions. You can recall when I talked about the earlier on about the cells. So when we talk about the oxidizing agents, reducing agents, and I said earlier on that the reducing agents, they tend to become, they are mostly metals. When I was talking about the first series, the first part of the series. So reducing agents are mostly what? Metals in nature. So the fact too, the non-metals are arranged in increasing order of reaction. That means we observe that as they're moving from here going down, the activity increases. The activity increases. So therefore, any ion, any half cells found at the bottom, they are what? As found at the bottom, they are more reactive in nature. The next one, fact 3, the metals above the hydrogen series do not occur in the free state in nature. Yes, yeah, they do not occur in the free state in nature. I think I was trying to explain something like that earlier. Instead, they exist as compound. That is true, because they are very reactive in nature. They are very, very reactive in nature. That's why those that are above the hydrogen gas, they do not exist in free state. What I mean by free state, you don't see them alone. For example, now, you see oxygen gas alone. You see hydrogen gas alone. You see nitrogen gas alone. Yes, that is true. They are free in nature. But the metals you have above hydrogen, above this hydrogen here, they are above hydrogen here, they are not free in nature. And that is the reason why you see them that they will be in few salts, they will be in or they will be in few salts, they will be in compounds. Examples of these are triazonitrate compounds, tricarbonates. The examples of all these compounds are formed that can be seen in above hydrogen here. Now, why? Okay, I said that earlier on. So, but you observe that the ones below hydrogen, metals like copper, silver, and gold, that are below hydrogen in the series, they are inactive in nature. They are inactive in nature. Funny enough, they're inactive in nature, and they are found in the free state. That's why you see them that they're in ores. They are in ores. You see that they're in ores. Example of such ores is copper. You can see copper. You see cassiterite. There are a lot of them. There are a lot of iron that are found in the free state. They are found in the free state. So the next thing you need to understand now is we want to create examples. We want to create examples of the examples based on how these electrochemical series work. What if we want to have different metals? We want to have different metals. So I want you to understand this concept. So before we go into that, I want us to quickly ask questions. So just take more of like a 3 to 5 minute recess for you to go. If you have questions, just drop it quickly. Just drop it so we can quickly go through that. Then we can have, I can want to quickly analyze the chemical series. So just short break, just short break. Just to quickly get that together. So we'll continue by 11:00. So we're back from our break. Now, let's look at those. Let's see how we apply to the chemical series now. Because we said earlier on that when we have a more positive reduction potential, such serve as a cathode, more positive. So you need to understand this. More positive, that is what? The cathode. Why more negative is the anode. That's why you observe that. That means with the chemical series that you have, the top, they are mostly positive in nature. So that is the cathode. The top are mostly positive, that is cathode. The bottom serve as the anode. So example of this is that if you look at the zinc and the copper, you observe what we're trying to see there. Now the zinc itself is minus 0. Is plus 0.76 volts, and copper is minus 0.34 volts. Now from this, let's say for ideally, I don't even know which of them is the reduction or the oxidation of cell. This is more positive. More positive. That means if it's more positive, this will be the reduction. That is the cathode. And if this is more negative, this is the what? The anode. This is the anode. And with that, we can get the E naught of the reaction. That is the EMF of the cell. And that is what is E? You know, that is what E cathode minus E anode. I've given you like about 3 same formula. Either reduction minus oxidation, you see the same thing. The cathode here is zinc, that is 0.76 minus open bracket minus 0.34 volts. And this will give us 1.10 volts. So you have minus and minus is what? Plus. So 0.76 plus 0.34 volt is 1.10 volts. 1.10 volts. And with that, you are able to get what they call the EMF of the cell. That is the E naught of the cell. And you can see how we've applied the chemical series to today. Next class, we'll round up this with corrosion and electrolysis. That's your time, guys. See you next class.